All right, so this is the sort of a sequel to section 6.8. You have just learned the last of the many theorems in chapter 6, and that was the divergence theorem. All right, so this is basically all your integrals summarized together along with its theorems and concepts. And I do want you to also um, learn the picture that goes with each of these. Okay, so let's start with number one, the line integral. Um, what is a line integral? And how do you find the line integral of a real valued function? So here the assumption is you are given f, which is a real valued function, and the curve. Okay, so curve is of course always parametrized by, you know, uh, t, and t goes from one to, sorry, not one, a to b. Okay, as t goes from a to b, it parametrizes this given curve c, and that's something you learned back in chapter 3, I believe, right? The line integral of f is, remember, you integrate not in terms of s, but you always use that parameter t. So do you remember what this was? You write f, which is written in terms of xy, but now you rewrite that only in terms of t. And then you have to insert something, right? And that was the curve, the speed of the curve, which is basically you take the derivative, and that's the velocity, and you find the magnitude of the velocity. That is what we call speed. But you have to make that adjustment because ds, remember ds was ds dt dt, and this ds dt is called the speed. So you take the derivative, find the norm, and that's what you will have to do to evaluate a line integral of a real valued function. This was in section 6.2 in our OpenStax textbook. Also, in the same section, you found the work integral and the flux integral. The work or the flow or the circulation integral, all the same, is when you are given the vector field in a two-dimensional space, otherwise known as a plane. And so your vector field will be written as PQ. And of course, F has an arrow on top of it. You have the parametrization. Okay, same parametrization. C is parametrized by curve. The parameter T that goes from A to B. This because when you're trying to find the work or the flow or the circulation, you're finding the tangential component of F, right? Always finding the tangential component of F because that's the force applied in the direction of the motion. And so this replaces what used to be this F, a real valued function. After all, F dot T is a real valued function. But remember, F dot T, see, you have to take F and dot that with T ds. And remember what T ds was? Because in order to find t, you just basically find the velocity, differentiate it. And then you normalize it by dividing r prime by its own magnitude. But ds also has this speed in here. Remember how it worked? This cancels. And so that's why you are allowed to write this in terms of, like this. And this is p dx plus q dy. The way to calculate this using your parameter t is to write f in terms of t. You dot that with r prime and then dt. Okay, so I hope you still remember how to do that. This is a standard work integral or the flow integral or the circulation integral. And then we studied the fundamental theorem of line integrals. This happened in 6.3. And so we assume that f is a conservative vector field. And if it's conservative, by definition, you can find a potential function whose gradient is capital F. Then the line integral, which is the FDR, independent of path, is equal to f of b minus f of a, where c is any path or any curve from a to b. So you have this curve, and we don't care how c gets from a to b. As long as c is any curve from a to b, you can use the fundamental theorem of line integrals to find the your work integral FDR, right? So that was the fundamental theorem of line integrals. Then we go to Green's theorem in the next section, 6.4. There are two versions of it. Let me just give you one version of it here, which is the worked version. F is given, which is a two-dimensional vector field written as PQ. And then you have, in this case, you have an XY plane, and you are given a region, simply connected region R. And that boundary is, of course, a simply closed curve, a simple closed curve. And we call that simple closed curve C, which is always a loop, right? And we oriented it in a counterclockwise direction. And then we say the circulation integral or the work integral over that curve C, which is the integral FDR, often written in this notation as well. But that is equal to, remember what this is? The double integral. Oh, I think we use D for this. Okay, of quicks minus pay dA. Okay, so that's how you can find the integral, which represents the circulation or the work over the boundary curve C. And of course, if F happens to be conservative, then QX and PY are the same. So this will be trivial. It's going to be 0. And of course, if it's conservative, you pick FB minus FA, but the curve starts and ends at the same point. So that's going to be 0, again, trivially. All right, and then we talked about the curl and the divergence of a vector field. That was in 6.5. And so the curl was defined as you have ijk, partial x, partial y, partial z. This is called the partial operator. And then you have PQR. That's how you can define the curl, right? And it is a vector valued function. The divergence, I should have arrows where an arrow is required or should be there. Okay, so the divergence is the partial of x with respect to x, p with respect to x, partial of q with respect to y, and the partial of r with respect to z, and that is real valued. Both of these will become more important as you go into the next sections, right? In section 6.6, we talked about surface integrals. Remember, this was a long section, parameterization of a surface. And once you parameterize the surface, here is your surface S. Now it sits in a three-dimensional space. The area is going to be, and the definition of area is simply the double integral of S ds, okay? But in order to calculate this, you had to, go back to the UV plane, and the region was D, and you integrate what? RU cross RV. So this is like your speed in the line integral. And this is what you would have to calculate in order to find the area of a surface S that sits in 3D. If you have a real valued function defined at every single point of this parameterized surface S, and the function, this could be like the density function. And in that case, this will be the total mass of the surface S. Is very simply, all you have to do is to put F in here, make sure F is written in terms of U and V, and then you multiply that with RU cross RV, or the magnitude of it. Okay, so this is how you find the density of the, the mass of the parameterized surface. Okay, now the flux is different. The flux actually, you have to find the normal component of it, not the tangential component. By the way, when you have a surface, we don't talk about tangential component, right? When you talk about tangential component, you have to assume that there is some kind of a curve that you are going along or you are following along. And because the surface S is a two-dimensional thing, we don't talk about F dot T anymore, but we can talk about the normal component, right? So, you have the surface S, and you have a normal vector that comes out like this. And if the vector field is maybe something like, this, then the normal component is the dot product of F and N. And if you add up, or if you integrate the F dot N, which is a normal component at every single point of the surface S, then you do get the total flux of F across S. All right, so that's what we are doing here. And what happens when you do that? Well, notice here, NDS, remember how you find that normal unit normal vector? That's the way you find your unit normal vector is RU cross RV divided by its norm. But remember, ds is exactly the magnitude of RU cross RV dA. So these will cancel, just like, just like these guys got canceled over here. And so again, there's a quicker way to write this, which is F dot RU cross RV. So you see the cross product and dot product appearing in the same expression for the double integral here. That is the flux integral, all right? When we say NDS, this is what is sometimes called ds with a thick or bold face. Okay, that is what the vector s means. It's a normal, the ds. And then we went up to, or we went next to the 6.7, which is Stokes' theorem. What if green could fly? And it's the extension of Green's theorem into S now, which is a surface not on the plane, XY plane, but in the XYZ space. Now you are given a three-dimensional vector field, which is F, PQR, F is PQR, over the parametrized surface F. It should be S here, okay, in R3 with boundary, which is a closed curve C, right? So the picture again is like this. You have S and C is the boundary curve oriented clockwise with respect to the normal vector, counterclockwise, right? And so this FDR, that is the circulation around the boundary curve C, is equal to the double integral of what? Not just F, but it's a curl of F dot ds, okay, which is of course, and this is over over S, and this is the curl of F dot RU cross RV dA over the region D, which is the, on the RU plane or UV plane. Okay, and then finally, we reached the last section, which is section 8, and that's where we studied the divergence theorem. It's a theorem where green gets an extra dimension. So now we have this object called the solid E, and S is the boundary surface. Okay, so again, this is the only one that involves a solid and the triple integral, therefore. Okay, given F, which is a three-dimensional vector field, just like in Stokes' theorem, but this time, unlike Stokes' theorem, which dealt with the boundary, the line integral around the boundary, this time it is the circulation. So this F and S are capitalized. So what we mean by this is, of course, F dot N ds. That's what the flux is. The flux of capital F across the surface S. That is the triple integral of the divergence of F dV. Okay, so this is often dx dy dz or dz dy dx or something like that. And so that is what we have. If you have a solid, okay, it's going to be clear. It's going to be the divergence theorem. Okay, if you only have a line, it's going to be either the fundamental theorem of line integrals or whatever. If you are to use Green's theorem, you have to have this region D, which is closed by a simple closed curve C. Okay, and so that's the difference between these theorems. So I hope you understand the difference, and it is important, I believe, for you to summarize and make a list like this, so you can have a big picture of the entire chapter, which has to do with the vector field, not just focusing on each section by itself. All right, great. That pretty much wraps up chapter 6 and the entire course. All right, and so do your homework, and then I will come back again to review chapter 6 in preparation for your test and your final. And so hopefully you've had a pretty good understanding of double and triple integrals from chapter 5, so you can use those methods in chapter 6. All right, I hope you you will get to this and that you will enjoy learning the last little chunk of Calculus 3. Take care. Have a great week. See you.